Hi, my name is Milad Beikbabaei, and today I'm going to talk about real-time simulation of an inverter-based microgrid with distribution management system or DMS. And this is the slides which gonna show the lab demonstration, and after that we're gonna show the software and the demonstration. This presentation is for Resilient Renewable Energy Grid Adaptation Laboratory Regal, and my supervisor is Dr. Ali Mehritisani. Here's the outline. First is the motivation, then we're going to talk about the RTDS, which is the real-time simulator setup that we have. After that, we're going to dive in and explain the 4-quadrant amplifier and the electronic loads which we have in the lab. After that, we're going to explain the implemented microgrid, which is modeled using the RTDS, the amplifier, and the electronic loads. And after that, we're going to discuss how the data is being exchanged within this power hardware in the loop setup. And finally, we're going to discuss how it's operated when it is grid connected and islanded mode. So we are having more inverter-based resources in the grid. The US have the goal of reaching 100% clean energy generation by 2035, and PV and wind turbine are connected to the grid through IBRs or inverter-based resources. This adds some challenges to the system, and to address that, we need to study the system. One tool that we can use is the real-time simulator, which can become very handy since 1 second of simulation is exactly 1 second in real time. And in this work, we're going to study a full inverter-based microgrid, which all the source of the generation can come from the inverters during the islanded mode of the operation. And this study has been conducted using RTDS in real time. So here you can see the setup that we have. On the left hand side we have RTDS PV5 technology, and on the right hand side we have the NovaCore technology. There's one rack of NovaCore technology and two rack of PV5 stacked on top of each other, and all these three units can work together to simulate a larger grid, and they're synchronized using the global hub connection. Also, the NovaCore technology give you some nice communication feature using the Giga Transceiver Network Communication Card, or GTNet in the short term. It supports TCP, UDP, Modbus, DMP3, and optic fiber. Here is the power hardware setup that we have. On the right hand side you can see the 3-phase 4-quadrant amplifier, which each phase is 2.5 kilobar, in total 7.5 kilobar. And on the left hand side you see that we have two electronic loads. The smaller one is 1.8 kilowatt and the larger one is 4.5 kilowatt. The amplifier support optic fiber and Aura protocol, and it's connected by optic fiber to the RTDS setup. And also the electronic load that we have can model the nonlinear behavior of the load, and also the real and reactive power can be adjusted in real time using serial communication. Here is the grid that we have modeled using the RTDS. As you see, it's a small microgrid consisting of a PV unit connected to the grid via an inverter. We have a battery energy storage system base that is also connected to the grid via an inverter and a transformer. You can see we have the physical load. So by physical load we mean that we have the 4-quadrant amplifier that is receiving its voltage from the grid, and it's connected to the electronic load, so it's physically the portion that is physically outside of the simulation, the power hardware setup that we have. And the load within the simulation is modeled as a current source. The current is being measured and being sent to the RTDS via the optic fiber to minimize the communication delay. Also, the RTDS sends its real power voltage measurement during the simulation using GTNet and TCP/IP protocol to a PC which is running a Python code, which is basically our distribution management system, which decides that we have our critical load connected or not. and the load value is being adjusted throughout the simulation using the serial communication. We're only using the 4.5 kilowatt load here. Here is the data exchange path of the testbed. As you see, the RTDS is sending the real power voltage breaker status to the network switch pass it to the router, and the router pass it to the server which is running the DMS. Also the DMS runs and it decides to adjust the electronic load to keep only the critical load or have all the load. And the command is being sent through RS-232 cable to the electronic loads, and the electronic load is wired and it's hardly connected to the 4-quadrant amplifier. And the way that the DMS work is that it work based on the state of charge of the battery. So if it see the battery has more than 50% charge, what it's gonna do is support all the load, but as soon as the battery drop below 50%, it only support the critical load, so it would be able to support them for a longer period of time. And the serial communication, as explained, is used to adjust the electronic loads output in real time. So here is the graph of the runtime in the grid connected mode. As you see, the grid is connected. Every value that you see here is in megawatt. So the grid is injecting almost 87 kilowatt. The load is 140 kilowatt, and 126 kilowatt is being generated by the PV. We can adjust the temperature of the PV panel, the insolation of the light, and here you can see the real-time voltage and the real-time current of the load here. And here is the breaker status. You can see all the base is connected, and also the load is connected, and the PV is connected, and the frequency is 377, and the state of the charge of the battery is roughly 39%. Here are the waveform. You can see the voltage, which is shown using the yellow curve, and and the blue curve is the current. You can see the load roughly is using 1400 watt since it's a scale down, and it's injecting the amplifier almost 1410, and the additional 10 watt or 9.8 watt is being dissipated through the heat, and it's the loss of the cable. So here is during the islanded mode of the operation. In the islanded mode of the operation, as you see, the grid is almost injecting zero amount of power. We have increased the insolation of the light in this case to 1000, which has almost doubled the PV generation to 250K. However, since our state of the charge of the battery is less than 50%, here is 37, the DMS will reduce the load to 60 kilowatt. And you can see also the instantaneous voltage and current here. So here, as you can see, are the waveform on the scope, which is directly connected to the 4-quadrant amplifier, and as you see, the voltage is almost the same, but the current has reduced compared to the other cases. And you see it's roughly 600 watt on the loads, and the amplifier is injecting a little bit more, almost 1.8 watt more, and that's due to the loss of the cable, as mentioned previously. Thank you for your attention. Now we're gonna record another video and combine it with this one, and there we're gonna show the software and the real demonstration. Here you can see the runtime of the RTDS, and as you can see, the simulation is being run in real time. Here is the frequency of the switching. You see we can change the insolation of the light. So if I change it to 500 rather than 1000, you see it changed from 2500 to 1262, and it's in the grid connected mode. The battery is charging, the state of charge of the battery is increasing, and the load is 1400 almost. You can see the voltage of the RTDS and the current, and the simulation is running. Here is the frequency as well, and all the components are connected. We are in the grid connected mode. So if I switch to the islanded mode of operation, since the state of charge of battery is less than 50%, as you see, the control level load will be disconnected and it will be reduced to 600, the physical load value. And the grid is almost zero, the power that is injecting to the grid. And in this case we have some extra power from the PV, so it's still battery storage system is being charged. However, so as you see, the current has been decreased as well compared to the past, and the reason is that we only have the 600 watt load. So if I reduce the insulation light of the battery even further, let's say 250, then you would see, or let's say 100. So then you would see the battery storage system would take care of the load, and now it's start discharging. And if I reconnect the circuit breaker, as you see, the grid would take care of the load and the charging of the battery storage system. And if I refresh, you see the magnitude of the current become twice, almost twice larger, more than twice a little bit, and it's the simulation. And this is the runtime. And if I switch to the model, you can see that here we have the amplifier model, we have the TCP/IP socket client model. Here you can see that we have the battery storage model, and also here you can see the PV panel that we have in our simulation. Thanks for your attention.